we've grown into a thriving community of over, I think, over 1,000 followers from all across the world. So on behalf of the entire team, I just want to say thank you. Thank you for your enthusiasm, for your curiosity, and yeah, for your commitment to exploring how technology and AI are shaping a better future. So, what better way to, close the year than with a session that truly um, captures the heart of innovation, um, AI for accessibility, transforming airport transport with smart wheelchairs. So, air travel can be challenging, especially for passengers with limited mobility. But artificial intelligence is changing that story. So from autonomous navigation to intelligent mobility design, AI is empowering travelers with greater independence, dignity, and freedom of movement. So today, we are honored to have with us David Nyako, a doctoral engineering student and graduate research lead at Morgan State University in the US, and the driving force behind the groundbreaking BWI Airport Autonomous Wheelchair Project. So David is an award-winning innovator whose work in applied AI and robotics is pushing the boundaries of what exclusive technology can achieve. So in today's session, David will take us behind the scenes of this pioneering project, sharing insights into how AI, robotics, and computer vision are reshaping airport transport. So that is the real world challenges of accessibility. So without spending too much time, I think I'll just leave the platform for David. And so, David, the floor is yours. Just a minute before David comes on, just a little bit of house rules. Please, for the next about 30 minutes or so, half of the entire session, David is going to do his presentation, and we are not going to interrupt with questions. And halfway through it, we open the floor for questions, and just a few of them actually. And then Prince will continue, and once he's done, we will continue with the Q&A session, and until we wrap up. So, David, the floor is yours.
All right. Thank you. Just to check, can you hear me clearly?
Yeah, it's clear. It's loud and clear. Yep.
All right. Thank you. Thank you for inviting me to speak. And a lot of greetings from my lab, Deeper Lab from Morgan State University. And yeah, like Kwame mentioned, I'm a doctoral student at Morgan State University, and I'm the graduate student research lead on this autonomous wheelchair. At Deeper Lab, we worked more on AI, machine learning systems that help with the equity concern and security concerns about the AI tools. And this wheelchair is no exception of some of the projects that we work on at the Deeper Lab, which is Data Engineering and Predictive Analytics Lab, which is under the Center for Equitable AI and Machine Learning Lab at Morgan State University, which this project is a partner of. So you can see the two labs linking there, the National Transportation Center at Morgan State University, and then the Center for Equitable AI lab. So I do a couple things. I do lead other projects within the lab. I work from autonomous designs to building AI, ML architectures for projects such as these autonomous wheelchair work.
David, I think
Yes,
we
sir.
lost you for a second. Could you please step back? I think that the internet was, I don't know if it was an internet issue. The last
Okay.
couple of seconds, I think we lost you there. So if you could, I think you just
Okay.
mentioned the two institutions that work together on the project, and that was it. Yeah.
Right. So it's the National Transportation Center is one of the labs at Morgan State University that works with the Center for Equitable AI and Machine Learning systems, which is seamless. So these two labs at Morgan State University collaborate to work on this autonomous wheelchair project as well. And as part of my contributions to the lab, I do more of uh, full stack development, building AI uh, algorithms into software tools that helps for the lab project. And one example is this autonomous wheelchair that I'm going to walk everyone through this webinar. And I've worked on a couple projects, autonomous hydroponic system, which won the 100,000 US dollar competition award, Kwame mentioned as well. So most of the engineering technology, the software, and the programming we do at Center for Equitable, I should say, is one of the best lab, arguably, in the Morgan State University, is the Seamless Lab, which I belong to at the school. So part of the webinar today, the topic, AI for accessibility and transforming airport transport with smart wheelchair. I'm pleased to be speaking on behalf of my whole team from Morgan. And yes, without much ado, I'm going straight into it. So for a bit introduction and context to this, you can see that, yes, obviously air travel is a bit challenging. And then for the passengers that need assistance with wheelchair or mobility issues, or sometimes, yeah, they can walk, but then they don't have the strength to travel the length and breadth of the airport space themselves. And sometimes they need a manual wheelchair assistance to move across the space. And then for BWI Airport, which we're using for a pilot, yearly there are millions of travelers using these airports, but then the demand for chair does not meet the, say, the number of help available to even manually push the wheelchairs that are available at the airport. And a typical example is one of our PIs as a motivation for this project was at the airport with the mom, and then the hours they had to spend at the airport to wait on someone to come push them to the gate was a lot of time and the motivation enough to help contribute to this work as well. So yes, as our goal, that's how it came in to empower the independence and inclusion of these people who need the assistant at the airport and be able to navigate freely without any uh, obstacles to them or anyone relying so much on people coming to push them at the airport. So here's our problem. And then in my AI generated image here, you can see that yes, there are a lot of the wheelchair, but then it's just one person or two or five, not enough people to help assist with the wheelchair um, movement. It's not a cool job to do. Yes, people are doing it, but then even the number of people to do it in terms of the demand for this service at the airport does not meet it right, at least for the airport that we are operating at. So this one person is pushing two people at the same time. There are a lot of other people who wishes to use the same service, but will have to sit and wait, and they are waiting at the expense of their flight time as well, which they will have to come way earlier than they should have because of situations like this, or if they arrive late, and it's going to be a worse case if they don't have the assistance to even push them from gate to gate. So passenger mobility was one of the things, and then the long walking from length and breadth of the airport space, and then the time of waiting as well. So our project overview, Urban Flow. So Urban Flow is the name of our project. You can see me in the wheelchair, and that's Michael, one of our teammates, handing a ticket to me on one of our demos, which we had with um, the Maryland Lieutenant Governor and to the airport CEO and the Morgan State President and a couple of dignitaries at this event where we demoed the wheelchair demonstration to them. So this is developed by the Smarter Center, like I mentioned earlier, and the Center for Equitable AI and Machine Learning Systems at Morgan. And the design or concept is not we trying to build everything from scratch. So the wheelchair you are seeing here was a mechanized wheelchair, but then it was controlled manually. So you push the joystick for it to go forward, left, and right, but then there is no level of autonomy to those wheelchair. And as part of our motivation, we want to build a more cheaper version of these autonomous systems. Because if you compare to what is already in the market, because in Japan or even in the US here, some of these autonomous wheelchairs, they build them from scratch. They build everything together, but then no, our innovation and the patents which we have for this is as a retrofit. So we can take any mechanized wheelchair that is electronic Nick, but then manual powered. And then we can use our retrofit to convert this into an autonomous wheelchair with our retrofitted device in the future. If we have that retrofit device, just attach it to any mechanized wheelchair, and then it becomes autonomous for you to use as well. And it's been featured in a couple news outlets, and it's a statewide product and one of the main features for the Morgan State University. We're in the phase three testing at the BWI airport. We are about moving to phase four, where we are going to partner with In Conversation. So looking at airlines like maybe American Airlines, and Delta was one of the most recent mentions, which we could have possible collaboration with them to do an actual pilot to the use the wheelchair from gate to the airline terminal to board the flight. So for some of the key technical features that is on this system is our perception and sensors. So if you look at the wheelchair before, you could see how it did had a pole. That pole is just the lidar that is helping it create its map and then localize within the environment that it finds itself within the map that it creates with that. And then there is the cameras, because there are two different types of the wheelchairs that we actually have. There is the full track mode version, and then there is a trackless version, or a hybrid, I should say, where it uses the track mode uses the cameras to look down on the track to detect the track to navigate autonomously and uses QR code as nodes to help it with orientation and help it localize and know what part of the register of the track, internal track that it is in at any point in time. There is the slam-based path planning and the obstacle avoidance at that speed. So 2.5 to 4 is like the fast walking pace for a person. That's the average speed if a human was to be pushing a wheelchair in an airport space, you should expect that amount of speed for it to be moving with it. There is a QR code, Salmon, integrated to the mobile app that we have app development team actively working on. So you just walk to the airport entrance and then you should have the QR code that helps you make the request for this. The modes, the guided navigation, and ongoing free space autonomy. So here I'm just going to show like a visual flow of the track-based navigation that we have for urban flow. And with this track-based navigation that you're seeing here, so this is just giving you a visual understanding of what the tracks look like within the airport space. So see the old person at the entrance of the airport walks in. So this is like a feature of a ride hailing service, but then for like an Uber, but then for wheelchair service. So the passenger walks in at the door, it takes the phone, it scan the QR code on the ground, the wheelchair will walk up to you on its own autonomous, no one pushing it. It will pick you up. It will take you to the baggage drop. It will take you to the security checkpoint and then take you to the airline gate as well. Inbuilt internal logics, there is the LiDAR sensors on the footrest that is helping it do collision avoidance. And then there is the cameras that is helping it detect the QR code, and then the green tracks that are laid on the ground. And the QR codes have orientations to help it know if it is turning left or right at any junction within the nodes that it's being positioned at. So yeah, that is for the track base. And then there is also Visual Flow for a hybrid navigation system. And for the hybrid navigation system, you're seeing two parts of Urban Flow. So Urban Flow, that's the free space navigation. So you can see from node 1, 2 to 3, it's no track. It's using the map that it uses the LiDAR that was in the hanging on the pole to create the map of the free airport space. But then the 1, 2, and 3 nodes that you're seeing is just we still guiding the wheelchair that, okay, we know you can move freely with the map you have, but then follow this kind of path, keep to the wall. But then if there's an obstacle, you have the map of the airport, and then it's just able to reroute itself, create a new plan, and then go about the obstacle with a new path and then restore, but then end up in the final destination where it's supposed to be. So here for this hybrid approach, you can see from QR code 1 is where the passenger makes the request. The wheelchair comes from the airline or the docking station where it's automatically charging up. It comes and then pick the person up, take it to point 2 to take your ticket, and then do 3 to 4 to TSA for you to get screened and go through the security, and then go trackless behind the TSA as well. So this is a video demonstration that is just going to show the technical validity and the social impact for this particular project. And I'm gonna hit play, and while you watch this, this has no sound behind it. So just as the map you saw, there is a request that I made at the gate, and then the wheelchair drives towards me. And that's me. I sit in the wheelchair, and it would proceed to go to the airline gate too. So I pick up my ticket, and then from there, it would follow suit to all the rest of the steps that was shown. So you can see the LiDAR at the top, and that LiDAR helps it create its map. After creating the map, it does nothing. It's just helping it to be able to localize. And then there is a LiDAR under the footrest where my leg is. And that is what does collision avoidance. And there are a couple visual sensors around. All right, so that was the hybrid one. Now it's going to show you, it's going to show you with the track-based navigation. It's going to move from QR code 1 to 3 on the track. And you can see in this version, it's only using the camera, and it doesn't have the pole like the previous version that you saw. So the camera is what is doing the detection of the track. And it also has the footrest LiDAR that helps it do collision avoidance while it's navigating within the airport space as well. Right. So that was just a long demo show. And this same pilot that we were doing, we moved from point to point, gate to gate. We can go from this is around gate 17 around the BWI airport, and it goes all the way to the security checkpoint. And once it gets there, it's able to now also transition to trackless mode if that's how we want it to continue with the navigation. All right, so I would like to proceed from here. These are some of the design challenges and considerations that we went with. So in terms of environmental complexities, you can see there were a lot of lightning and reflections and floor texturing variations that we had to deal with because we're using lighters and, oh, excuse me. We're using lighters, and then one of the limitations for the lighters that we're using is with it being able to go through the glasses at the airport space. And let me, so you can see at the airport, you can see that with these videos, there are a lot of glass at these airport environments. So it's one of the limitations that we are facing at the airport with the lighters going through. So we are trying to work on other in-house algorithms that is going to help us overcome some of these hurdles. And we're using like monocular depth detection is one of the approaches that we're using, where it's just one camera that scans the QR code when you are boarding the wheelchair as a passenger. So that camera sees the environment, it creates uh, a visual perception of the environment, try to understand the environment in a monocular way. So monocular meaning is just using one camera compared to the two camera uh, real sense detections. So we use those to help fuse with the LiDAR detections to help it do the obstacle avoidance within the spaces so it's more accurate and reliable. There's the obstacle detections that we help and then help with the trust, accessibility, and dignity to help empower users and ensuring comfort within the space that the wheelchair tries to operate. But yeah, amidst these, I think we've worked so hard in trying to make sure it's um, more reliable, which is the main thing because it's an airport space. There are a lot of people walking, there are a lot of people doing random stuffs, trying to make sure the wheelchair can predict most of those cases and then understand those cases and try to create their own new path, new plan, decisions, and communicate to servers, whatever that is going on at any point in time. So for future outlook and impact, it's the deployment in hospitals and campuses and museum spaces. So one of the main collaborations right now is with the university nursing department, and then they have like a facility that is like one that the hospitals use in the US here. So we are going to test with those facilities of how the wheelchairs will be used in these hospital spaces and then campuses and museums where tourists just walk in and they have a checklist of what they want to see because it's the system and then it's mapped out of the place. You just on your phone give it those checklists. It takes you from point to point to these areas to see exactly what you want to see in time. And integration with the autonomous shuttle and ride-hailing systems. There are other projects. I believe is University of Maryland, who is also working on autonomous shuttle system that we are looking at trying to have this wheelchair be a collaboration with that to have a more autonomous uh, fleet of the buses and the wheelchairs. So you bought the wheelchair from the airport. It goes to an autonomous bus. It takes you inside. So there is that integration of the future, what is to come for the future, and the continuous AI improvement and prediction in terms of navigation and battery life to have um, it extended, which is one of the key research that we are doing within the lab space, and accessibility as a pillar for AI-driven uh, research in our. And this is the main team. This picture was taken at the airport when we did the demo. That's our president in the middle. And right next to me is the lieutenant governor who witnessed the project and the main demo, which was one of the main events that we did at the airport. So yeah, let's open doors and airports to more inclusive world has been our drive, and we just working for the future ahead. These are some of the faculty leadership and technical oversight. Dr. Kofi Nyako, he has the technical faculty lead and advisor for the team, and Dr. Jehani, who the actual product sits with her in her lab. And then it's a collaboration with her and then Dr. Kofi Nyako's lab, which is deeper, and the Seamless, which I currently work with. So yeah, I would say thank you.
Right. Wow. Amazing. Thank you so much. So,
Yeah.
well, are we taking a pause here and then you continue, or this is a wrap?
So this is like the wrap, and then I would rather want to answer more the questions into the time that we have. So I'm open to any
Right.
questions that anyone has regarding
Right. Okay.
this project.
So generally, what we do is we ask audience to write their questions in the chat, and
Okay.
then we'll read them out. But since we have relatively large amount of time, and um, I think we would open the floor to anyone who would like to ask questions. You don't necessarily have to put in the chat. We can unmute you. You probably just need to show a hands up that you have a question, and we will unmute you, and then you ask your question. But I have a few questions of my own. So
Okay. Okay.
while the others are preparing their questions, maybe I'll ask mine, and then we take it on from there. So we've seen the various modes. You have the track, and then I'm not sure how you call the other option, but almost like the fully autonomous one where it doesn't rely on the track. And I'm wondering how challenging it is for either one of them to be adapted in a new environment.
Okay. 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 So how challenging for one of them to be adapted in a new environment? In terms of comparison, I would say the hybrid approach will be the most challenging for adapting to a new environment as a whole. But then looking at the visual flow for a track-based navigation is just laying down the tracks. And so if I just walk in any random space, no matter what it is, and I don't even know what the reflections are, the glass issues are, all I need is to be able to lay my track down, the free space for it to, you just give me the space where it has to move. If it's a hospital, if it is a museum, we lay these tracks with these QR codes as nodes. It's just to follow these tracks and then use the QR code nodes within the map to help it localize and orient itself. So pretty easy to adapt in a new environment for a track-based navigation. And just to even talk about those tick counts that you see here as 200 ticks against 400 ticks. So the tracks, they have like we have encoders on the wheelchair that helps it know the distance that it has traveled. So we know the length of each track. So if we double it, quadruple it, however long we have a particular track for a particular long segment, all we need to have is the real representation of how long a track is. If it's uh 1 meter long, 2 meters, 100 meters long, we put it in the code base, or when we are creating the map, we specify the length of the map. And after we put the length of the map in in there, we make sure the QR codes are oriented in the right orientation and it connects together. So there's QR code 1 connecting to 2, connecting to 3, and then at 3 it connects to 5 and 6, 7 and 8. And it's like you're drawing the path in your mind. So if it's this QR code, when you get here, you have to go to security checkpoint, or you have to go to the baggage drop from here and from there. And that's just with the track-based navigation. Just follow the track that we lay. So moving to a new environment is all about knowing the distance, knowing the space, and then having where to lay the track. And yeah, before, one of the main issues would have been trying to deal with sunlights and reflections and shadows. But now they are no more a thing, because one of our main versions when we were working during phase 2 was we were using like only computer vision and trying to extract the track and then the QR code. So reflections were one of the main issues, where the wheelchair and then the sunlights were casting multiple shadows on this through the wheels of the wheelchair. And then it was difficult for the wheelchair to now constantly detect the track. And there were a lot of false positives in what it thinks the track was to keep to that route. But then, yeah, we worked on the deep learning model that gives it more instances of track when it was working with the computer vision algorithm. And we tell it, okay, these are the tracks, these are the QR codes that we want you to keep following. We're trying a deep learning model that would always be sure to pick up the tracks based off the features, even if it's occluded or there are shadows casting on it, it's still able to pick up the tracks and follow it well. So yeah, in an environment with random shadow casting, it's still able to pick it up and follow. But then with the visual and then for the hybrid approach, here is for any new environment, totally new, we will have to create a new map for that environment as well, which is pretty easy as well, but then not as easy as compared to just laying the tracks down and then having the wheelchair follow with the right encoding values. And yeah, so it would be able to create a map of the whole space, be able to localize at any time on its own, because localization is done automatically based off the logics that is in the software with the LiDAR that is hanging up as well. So you create the new map of the space and is able to navigate from point to point within the environment.
Right, right,
Yeah.
right. Thank you. Are there any questions? So if you don't want to ask in the audio, you can still type it and we'll read it out if you have any question. So if there are still no more questions, I think I have more questions.
Okay. I
Um,
love it.
so you mentioned about uh, challenges using the camera, and I think you also mentioned about challenges using the LiDAR, uh, mainly due to reflections and so on. And my question is two-folded actually. So
Okay.
in the first part, it, so Elon Musk argues that it's enough for a camera to drive an entire autonomous vehicle. And, you know, an autonomous vehicle drives outside with worse conditions than what you have inside the airport. Is that probably something that, we're missing here, something that probably you can adapt from the approach that he's using to enhance a camera-only solution. So that's the first part. And then
Okay.
I personally, with my background, as you are aware, in developing electronic control unit for driverless vehicles for uh, some time in Germany. We have I firmly believe that a camera alone solution, it's not viable. So we would fuse multiple sensors. So we would use LiDAR, radar, and camera. And I'm wondering, have you are you also considering fusing the LiDAR and camera, sensor outputs together and doing some sort of voting to decide on which which path to tow.
Right. Okay, so from the Elon Musk part of uh, a LiDAR against just the um, cameras, so impressively, I believe if the software is good enough, because as humans, it's just the visuals. That's his argument. Because if you're a human driver and then you're driving on the road, it's just your eyes to be able to make the visual estimate of where the obstacles and the objects are on the road. So for like a LiDAR, like we are using, and then it's having issues with the glass in the environment on the road, it's not a thing to have like a fully glass house in the middle of the road or exactly on the side of the road to have for it to be a main issue. But then yes, for the camera, we turn to apply the camera, and that's like the monocular depth cameras as well. So the depth cameras are good in trying to also help in do the distance estimations. And I believe he has done a couple big arguments with the camera cases. And then I drive a Tesla myself, and I do see the autonomous navigation and then how it has grown over time till now. And with the new release of FSD that came out, you can see all the uh, enhanced features that it has. That, yes, if it has LiDAR, it could have solved some of the issues as well. But then, yeah, like take Waymo, for instance. Waymo is doing the LiDAR part, it's doing all of these fusions you do talk about. But then yeah, but they all have the arguments they would tend to argue around which one is better. And then yes, for me, if you ask me, the Fusion is always better for me at the kind of software level that we are at. And yes, it's something that we are doing with the wheelchair because we have the LiDAR information under the footrest. And like I mentioned, there is the camera that is on the side of the wheelchair as well. That if it is not being used for passengers to confirm that it is them that booked the ride, it would be looking ahead in the airport space and then do depth estimation to be able to detect obstacles around using the cameras as well. And that is an active research as well to help do an ensemble of those two detections and try to, yeah, do the voting you did mention about. So, right. We do use those two, and it's a fusion is something that, yeah, we are interested in doing more of it as well.
But what's your thought on radars? Have you considered using radar?
So for radar, we haven't considered using radar as well. And then one main thing as well is as part of everything we do, having it be as cheap as possible, but then do exactly what the expensive versions that are already on the market do is one of the key things that we consider as well. So we want to use the cheapest LiDAR and then rather focus on building a tougher algorithm that would help solve the same issue with the cameras that are available. Because we could have purchased a depth camera and then use a depth camera in doing those depth estimations and all. But here in the case, we're just using a regular RGB camera and trying to write softwares to have the RGB cameras do um, monocular depth estimation to be able to work as if it's two cameras pointing out, casting out the rays, and then getting the values to be able to tell the distance of obstacles around the the wheelchair so it doesn't collide or go about them. So yes, yes.
Interestingly, that was one of my questions as well, because I was wondering why you're not opting for stereopsis, which would obviously stereo would mean using two cameras, than
Right,
going for the monocular option,
right.
because stereopsis in using the two camera solution would easily estimate depth and provide that information for yourself. So
Mhm.
it's mainly on price, for cost reasons.
Yes, yes. We want to be able to provide a cheaper option against any other alternative that is in the market at the moment. And that is one of the main motivation and one of the main drives for these. We obviously are doing other versions of the wheelchair as well. And then there are like a ROS version that we are also working on that is obviously going to have all these depth cameras and all these LiDAR sensors and working with the ROS platform. But I must say the current implementation is all in-house built and it's all in-house build and is built with uh how do you call it, the cost in mind to be able to rather improve on the same whatever we have, do the best out of it. I tell you, the main brain for our system is like a Raspberry Pi 4 for
Wow.
our wheelchair system. So a Raspberry Pi for running all these compute with the wheelchair in the airport. And it's doing exactly what we want it to do. And we are improving on it. We recently just talked about upgrading to Pi 5 because of the how do you call the compute that has been is like the Pi 4 is getting to its peak at the moment. So yeah, we're just gonna switch to Pi 5 to do more compute with the Pi 5 now.
Oh, that's very impressive. Implementing all that on a Pi.
Right.
So Derek, do we have any questions in the chat?
Question in the chat.
Okay, maybe right. I still have more questions.
Okay, okay.
Uh, so maybe if there are no more questions, I'll ask one more question. So you don't use the camera for object detection?
So for the camera, we do use it for so like the monocular depth estimation. It's pans from doing the object detection. We do segmentation, and through the segmentation, we get the segmented mask, and we do some processing on it to be able to get the depth. And based off the segmentation is that we have across the whole frame that the camera is seeing, we are able to point out the distance uh, of the detected objects based off its segmented mask. So yeah, we do object detection. We segment the detection, so we get the instant segmentation of the object that is detected as well. We use that to compare with uh, the surrounding pixels which is also segmented as well to be able to tell the absolute distance of the object from the camera. And yes, even with the track detection is an object detection algorithm that it uses. So it detects the track and then but then it looks forward ahead and then to tell the change in orientation that the track has to be able to orient back on it and then away from it to move with that. But then that's the detection and then segmentation because we are concerned about where the green track actually lies within the track. So if you have uh with with the wheelchair and the camera, like I can actually forward this. So this camera here does the detections as well, which is helping it do the monocular depth estimation. And there is a camera that points right on the ground, which is under the wheelchair where the LED strips are that looks down all the time at the track. So there's object detections that helps it detect these QR codes and then the tracks that is orienting onto as well. And I should say that there are other team members. So like I should say Derek. Derek is actually working on an algorithm, an object detection algorithm to help it track the passengers that are going to board the wheelchair. So if I walk in front of the wheelchair, I have my phone. The detection will first capture whoever is holding the valid QR code and then we'll track the person who is holding that QR code after you are even done scanning. So it tracks to ensure that the right person sits in the wheelchair and not any random person will sit in the wheelchair. So you scan it, that is an object detection of detecting the QR code. And then after it detects you and the QR code, but then it would take the region of interest. Okay, so it was this person holding the QR code. So I need to track this person for him to be the one sitting in the wheelchair chair. And then there are other platforms that we are building that is going to carry the loads, the baggage that the person brings on, is checking bags and all that. So that platform should have an algorithm to track the wheelchair that the passenger is going to sit in as well, which is a design that we are still actively working on as well. And there is a version that was recently talked about where it's going to be retrofitted onto the wheelchair that is autonomous. So it's just going to move freely with some axial wheels and then follow the autonomous wheelchair anywhere it's moving as well. Yeah.
Wow. Impressive. Impressive. So, are there any more questions? Or Derek, do you have any questions yourself? Okay, Derek.
No, I think all my questions are answered. And
All right, okay. I might have one more. I'm wondering, you do segmentation, you said, and based on my previous experience, I'm not sure what algorithm you guys use, but for the lane prediction, is semantic segmentation something that you're considering,
So
like
for the lane,
FC8?
right, for the lane segmentation, what we are using right now is instance segmentation against semantic segmentation. So because we are not just detecting the tracks, we are detecting the tracks and the QR code as well. And we need to have unique IDs to whatever the track that is being detected or the QR code that is being detected. So if I come somewhere here, in an internal map for the wheelchair, there could be a track that goes forward, and I can even use this diagram. I could use this diagram here. So you can see the wheelchair is moving forward here. So after the QR code, there is a track after the QR code. And then to the right of the wheelchair, there is another track that branches there. Say the wheelchair is supposed to branch onto that wheelchair and not go straight. We need to be able to detect the tracks and not as semantic segmentation, but instancing provide unique IDs to the different tracks that are being detected. And while it walks up to the QR code and the tracks that are beside it and ahead of it, it used the orientation and then the new semantic instance of the QR code that is being detected to know that, okay, I'm at a new node. And at this node is going to detect 3 instances of the track and not a semantics to treat it as one track on the within the map. So it gets the semantics instance segmentation of the track. And then, okay, at the node, based off the QR code orientation, it knows to turn right at this QR code. So at the right, there is a track instance tracking ID that is assigned to that track. So it will know which track to be sure to turn onto and not follow the straight line. And that would be an issue if we are using a semantic segmentation approach for this logic. But yes, for semantic, we do use semantic segmentation. Sorry, for the case of the monocular depth estimation.
Right. Great. Great. I think I've exhausted all my questions.
Okay.
I had quite a few of them, and then you've answered them all quite well. I'm quite impressed. So,
Right.
one more time, are there any more questions? Otherwise, I think we're wrapping up about 7 minutes earlier than planned, which I think
I
is
guess I
fine.
might have done the shortest.
Nah, it's been quite impactful. I've enjoyed it, and I'm sure our audience have as well.
Right.
Um,
Because urban
yeah,
flow is big. There are bigger pieces of urban flow, and we could go on and on and on. And I believe specific questions, and then what part of it will help like bring the different individual pieces of the product
right,
as well. Because I could talk
right,
about the server side, I could talk about the fleet of the wheelchair and how we are planning to have it, like a lot of it within the airport space, passenger request for it, the wheelchairs, being able to model with the model that we intend to build, be able to say, okay, this is the wheelchair that is available. Go pick up the passenger, your base of the battery life that is left, base of the distance that it's going, base of the drop-off points. So it's more optimized and yeah, could talk about the different collaborations to the different for the
So
wheelchair.
when you mentioned server, something came to mind. I think about 7 years ago when we were one of the um, topics that came that was quite loud back in the day when we're working on the ECUs was the idea of building ECUs at the edge. So having a compute system, you using a Raspberry Pi. Well, obviously for a driverless vehicle, you need a bigger platform at the edge versus having the system running in a cloud in a server somewhere. The obvious challenge is the latency, induced latency in transmitting the sensor data from radar, lidar, camera, etc., to the cloud and getting it to compute and bringing it back. Now
Right.
that is quite reasonable if you're considering a car driving on a motorway 50 miles, 60 miles, 100 miles per hour. But in your case, where you look at 2.5 miles to, 4 miles, and cost is an issue. Have you considered running the compute on a server nearby? So you gather the sensor data at the edge and then transmit it to the server. It does the compute, extrapolate information, and then send back decisions.
Right. So yes, there's been multiple conversation around that. And I would say even currently, like I mentioned earlier, it's about optimizing what we have. And with the Pi 4, most of the computes are done on the Pi 4. So the optimization algorithms we write to make sure it's able to handle all of that. So yeah, latency and then security concerns as well. So each wheelchair is going to operate at its own individual node. So yes,
Mm,
so a server crash is not affecting all of it, but then the the wheelchairs do communicate through the server, but then with the uh, microcomputer that it's running for itself, there is the algorithm that each wheelchair will be able to be self-dependent. It's well optimized to run on its own with the compute that we have. So be in this case, it's going to be Pi 5 eventually. And then the server is just going to transmit and then do the server side uh, wheelchair to clients, clients to admin, admin to wheelchair communications, knowing where the wheelchairs are at any point in time, tracking it, getting the information, bringing the request to the wheelchair, and then having it shown to the admin to see it. But then yeah, for like a future deployment, or if like say it was like a micro ROS experiment, which has been tested with that regards, where the compute was done on a bigger server that had bigger compute, and then the wheelchair was which wasn't a general test for the wheelchair, but then it was just one test case to actually communicate it. But then, yeah, it's something we've done before, but not something that we want to do when we are trying to scale the wheelchair as a whole. Because, yeah, right.
great, 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 great. So I think now I've really, really exhausted all my questions.
Okay, okay. And that
And
was really on time as well.
exactly, I think we've made very good use of the time. Thank you so much,
All right.
David. It's been amazing. And thank you very much to our audience as well. So,
Right.
yeah, once again, we're coming to the end of another successful webinar. Very informative. Thank you to David and his team. And we wish you all the best for the rest of the time in your PhD research. And we hope to have you here again. So thank you very much, and
Right.
to our
Right.
audience as well. And have a wonderful evening, and see you next year. All right.
All
Okay.
right. All right. Thank
Bye.
you too. Thank you for having